And we said that the thermal rule usually happens for it's usually important for VSO. For edge emitting layer, since its space is large, so before the thermal rollover, there will be another failure mechanism. Might happen first, and it is non-reversible. It's called the COD, catastrophic optical damage. This is what it happens. When the output power is high, you have lots of energy will be reflected on your side mirror. And if your mirror, your facet is not so flat, probably you have only few steps or a particle on that. That will make the electric field specifically high at such a point. So with the specific high peak electric energy, that will heat your particle or heat your shape irregularity at some point. So it's called the local heat. And when the heating is high, the band edge will shrink because the normalization effect. With a smaller band gap, it will also further increase your absorption coefficient. With higher absorption coefficient or more energy above that, the original defect might propagate or trying to increase. And so your defect density increases locally. The low heating becomes even higher at the such point. So it forms a dead circle. Then the whole facet just explode. Until when so after the facet is burnt, because of this kind of recycling energy, you will get a lot of the defects at that point. So your reflectivity reduce. Then your mirror loss increased a lot. At the beginning, you might have R is equal to 99% by multi-layer deposition. But after such cycle, your oxide deposit on it might just keep. Then you don't have such high mirror anymore. Then your laser doesn't lace anymore. So this kind of failure is irreversible. Once it happens, your device is dead because your good mirror doesn't exist anymore. So the IV curve will look like that. It will increase, and you see that the slope is actually slightly decreasing due to the thermal rollover, but not reach its maximum yet. But to a certain point, it just directly goes to zero because the mirror is damaged. Then if you try to measure that again, now it doesn't return to the original curve. But for the thermal roller, this is reversible. As long as you turn off the current and let the sample cool, it will return to its original site. So this is called a catastrophic optical image. This is also a principal failure mode, which limits your maximum output power for edge emitting lasers. So what you can do is that only about the processing. Since the heat dissipation is not a dominant issue, you need to stop everything here to prevent a local heating. As long as you can let the whole facet to bear the energy reflection at one time, you will delay the COD to a stronger energy density. So what you can do is try to optimize your processing, or try to clean that, or try to deposit another certain layer to make the surface to be stronger than your original test surface. So although this doesn't has nothing to do in the homework or midterm, but this is a real issue for company making high power lasers. All right, so let's go to the final next slide. So we learned the rate equations of the laser diode. but large number of them cannot be directly measured. For example, how do you know the injection efficiency? Do you have a probe buried inside your content well to really count 1 electron, 2 electron? If not, how do you know the exactly injection efficiency is? Yeah, surely you can make a guess or make a simulation, but do you have the experimental method to calculate the delta I and the alpha? Since alpha n can be evaluated as long as you have the cavity length and you know the reflectivity. Since optical simulation is usually pretty precise, if you have the reflectivity or you have the reflecting index, you can calculate the R1 and R2 pretty precise. So you can evaluate the alpha from experiment. But how do you evaluate the internal loss and the injection efficiency? So that's scientists probably 30 years ago, they're trying to do that with something called varying length method. What they do? They make a epi wafer with laser epi and do the process to make the cavity length with different lengths. For example, he made one with 600 micron, the other with 800 micron, and some with 1000 micron. Something like that. So, for those with a shorter cavity, you have a higher mirror loss. So, you will have a higher mirror loss, you will have you can still extract in zeta d here. And you have a longer and you have a lower alpha n, then you have another slope. Alright. And we know that the slope zeta d is equal to zeta I times alpha n divided by alpha. And further expand alpha n, you will look like this. Then we take a inverse. We can plot the slope in zeta d in inverse under different lengths. Then the slope will be alpha divided by zeta I times natural log 1 over R1, R2. And the intercept will be 1 over zeta I. So we can evaluate, since we have its intercept, we can solve zeta I. We have zeta I, R1, R2, we can calculate its internal loss. So we can really try to evaluate the internal loss and the injection efficiency via experiment. So this is the case, for example. They do the single quantum well case with different cavity lengths and the double magnetic. There's a risk that if your cone is not large enough, each one always has some error here. So if there's an error, that will significantly change the intercept around here. So it is possible to get an injection efficiency larger than 1. But it is not physically sound. If you found that the 1 over zeta I is less than 1, that will be problematic. So this kind of measurement is actually risky. You need to find that the fittings will behave. And your cutting of different lasers at a different area should have no precision effect. That means your laser must have a pretty good uniformity. Or you cannot compare the laser at one side to the laser to the other side, and then will be a problem way. So it sounds pretty straightforward it sounds pretty straightforward. The research. If you can generate a figure like this, you can publish a paper at applied physics later or above. Yeah, I have the senior just trying to really grow every wafer. After lacing, he don't know what to do. He just change the mask to make a lens with different one. And finally get a figure like this, and he published in APO with a very short period of time. But the whole procedure doesn't sound that elegant, because sometimes you will get a figure which doesn't look pretty reasonable. Yeah, so this is actually experiment really limited by your processing capability and the sample. And the other way to evaluate the internal parameter is called the Hardy-Poly method. Hardy-Poly method, what does that mean? Because we know while the device is nearly lazy, we said that there will be two brackets, one at higher side, one at lower side. For those one at higher side, the round trip exponential 2j beta LA is equal to 1. So it means it's constructive reference. For those at the lower side, those point reaches lower point, it's because the round trip reach pi, not 2 pi. So the exponential 2j beta ALA is equal to -1. And we know that the intensity you measure is actually the square of your electric field. So you have Emax be E0 times R1, R2 exponential around trip times L. And the whole term is equal to 1. The J beta is equal to 1. Then N summing from 0 to infinity. So it is an infinite series. So it will be something relevant to 1 minus R1, R2 exponential gamma 3 minus alpha L. For those lower limit, it is a round trip is have a -10 here. So the total field at the lower bracket is equal to 1 over 1 plus R1, R2 exponential gamma 3 alpha L. And you see that you take E as square I. So this will be square root I minima, which means the underlying the low bracket or the low envelope, and this is the high envelope. So the left hand side becomes square root I max, and then compare both sides to a rearrangement. You will get gamma G in terms of lambda, because you can extract every point with different wavelengths. And under different injection current, because you can extract their near lacing with an acceptable injection current level. That will be alpha times alpha n divided by 1 minus L. So the bracket here minus minimum bracket times maximum bracket plus minimum bracket. Okay, so we calculated with different wavelengths and calculate with under different gain. We can really measure the optical gain under specific current injection level. Then you can get a curve like this. For example, under 20 milliamp, the modal gain is around 6% squared. So if you can also generate a figure like this, this will be another paper. But this is also not requires a lot of the data interpretation and the calculation. So if you can that definitely can publish your paper, but you also need to work hard. Alright. So while you have such model get with the current density, you can either figure out, do a curve fitting with the two model case. You can finally get how the G0 comes from. So G0 can be also experimentally measured. Gamma can be done by optical simulation. So you can try to put everything together, trying to really characterize your laser diode. Okay.